Hello everyone, I'm very happy to host Tomer Berg here. Tomer is currently in his PhD studies in electrical engineering at Tel Aviv University. His research focuses on problems of information theory, statistics, and communication. He is a recipient of the 2020 Weinstein Award for Excellence in Graduate Studies, the Jack Kyle Wolf Student Paper Award at ISIT 2020, and the 2021 David Bernstein Paper Award. So today we'll talk with us about deterministic finite-memory bias estimation.
Okay, thank you, Elad. Hi, everyone. Everyone can hear me okay?
Yes.
Okay, so as Elad mentioned, today we'll talk about deterministic finite-memory bias estimation, which is a joint work with my advisors, Or Ordentlich, 007, and Ofer Sheevitz from Tel Aviv University. This presentation is based on a paper we submitted to, we presented in the recent COLT conference. So I will start by describing the problem that we are looking into. I will give some relevant related work, and then I will describe what is a result, what is actually we're achieving in high-level overview, and then we'll go into technicalities, but I think not too much. Okay. So let's stand over here. Maybe the battery is. Thanks. Okay, so we consider the following bias estimation problem. Consider the following sequence of independent, identically distributed random variables, okay, xn, which are drawn according to the Bernoulli theta distribution for some theta in the unit interval. And we're interested in estimating theta under the quadratic loss. Now, we do not limit theta, or we do not assume any prior distribution on theta. So we are not in a Bayesian setting, we're in an adversarial setting. And thus we're interested in the minimax risk, which is the best worst case risk that can be uniformly guaranteed for all theta. Okay, and it's defined by this minimax. Now this is a classical problem, and it is well understood when memory is unlimited, right? The optimal estimator simply looks at the number of ones and normalize it. So we simply count ones, right? And we can get, as the sequence length grows, we can have a quadratic risk that goes to 0 with the length of the sequence. However, if the sequence length is large and we have limited memory resources available for computation, then this optimal rule can no longer be implemented, right? Because the size of the memory is about order of log n, and this grows with n. So we are talking about. Yes. Why what?
Why the memory is growing the same?
If you want to use this estimator, you count the number of 1 in a sequence of length n. Then you need about log n bits in order to, just to do the counting, right? Okay. Yeah. Yeah, sure. But you still need to count. I mean, either you stop. You can decide to stop at after seeing m samples. But if you want to use the optimal solution, then you will need to count as long as you have, because otherwise you're just throwing samples away, right? But you have an infinite number of samples. Consider that n is very, very large. N is unlimited. You cannot even, if you will have an infinite number of time of doing this update, right?
So I have a question about the motivation in this question. motivation to study this question, because take 128 bits, which is nothing, and then you can have n to be 2 to the 128, which is more than what I can think of. So who cares?
Well, I think, when you consider such estimation tasks, then you want to give a solution to this task. You're thinking about practical estimation. You say, okay, if this is very large, then who cares? But first of all, we would like to solve this, and this is what we're doing. I mean, my background is mainly in electrical engineering, I must admit, and this is very common to ask these type of questions over there, and I think also in math, right? If you have a large samples, what is the optimal estimator that gives you the best risk that you can get? Now we have the added limitation that we limit our memory to be, let's say, m bits. Okay, we're going to use states here instead of bits, so we'll have s states. And we want to ask the question, what is the optimal solution under this restriction? And I think maybe the next slide will refer to what you said, to what you're saying. So traditionally, when you look in this estimation task, then the way to characterize this problem is by something called the minimax sample complexity, which is the minimal number of independent samples we need to see in order to estimate theta to within a certain minimax risk. However, it seems that as the amount of data is constantly increasing, then it seems like the number of samples is not collecting enough sample to accurately estimate theta is becoming less of a problem, and it's the computational resources that we dedicate to this task that become the bottleneck, right? Computational resource can be limitation of memory and communication and so forth. And we focus on this problem. What is the optimal solution in case that we have a limitation on memory, right? Now, in order to focus only on memory, we allow the number of samples to be arbitrarily large. So we assume that we have unlimited samples, but the memory is finite. You have s states or log s bits. And the question is, what is the optimal solution? And it turns out that even if you assume n which goes to infinity, if your memory is finite, then you don't get a trivial solution. There's no trivial solution to this problem. It is very interesting, and it is not clear how to solve it under this restriction. Okay, so the setup here is you have as many samples as you want, but the memory is limited.
So let me ask about the trivial solution and what's wrong with it. Okay, so the trivial solution, say that 128 bits is fine. Okay, so the trivial solution is take only a subset of size 2 to the 128 samples from your unlimited samples, estimate theta based on it.
Okay.
Way, just average.
Yes.
Your error will be 2 to the minus 128.
Okay, so but you can have 128 bits. Maybe you have 1,000, but maybe you have 10. Maybe you have 5. Maybe you have some application that does a lot of tasks in parallel and can have only a small amount of bits or memory allocated to each task. So we still want to understand what is the optimal solution in this case for.
So this is my question. Do you have any real world application to this? Is this motivated from something real, or is it just it's fine that it's just a mathematical play?
Yes.
But I want to.
I haven't yet introduced what it is that we're showing, right? I'm just in the background right here. So
maybe you can try to answer that question. So, okay, first of all, it's mostly mathematical problem. But there are some practical motivations in IoT that sometimes you want to track any parameter and the sensor derivative. So if you don't get even 128 bits per parameter, because there's many of them. That's not the real story. The real story is estimating under memory constraints is a very important problem. You agree with this, right? And this is the most basic instance of an estimation problem you can think of, and even this is not understood. So that's the main one.
Can you give some two examples which I encountered when you write the chip for like every bit counts, so we need to do less bits each עברית. כשמייצרים צ'יפים לסמארטפונים וכדומה, אז כאילו יש כמות מוגבלת של ביטים ומאוד מאוד חסום, השגיאה שם מאוד מאוד משמעותית, לפעמים אתה צריך לחשוב באמת מה אתה יכול לצפות. ודוגמה נוספת זה מחשבים פרקטיים, שיש שם ממש כמה סדר גודל של כמה עשרות. ואז כאילו, אתה רוצה לבדוק
So, I will play along.
באמת, אם אתה מחפש פה את האפליקציה של פה, כמה משתמשים בזה גם, החלק של העבודה. ובעיקר, יש פה בעיה שהיא מאוד חשובה של מידת החטיבוצי זיכרון, וסאמפל בדרך כלל. בואו ננתח פה את הסאמפל וננסה רק להבין מה האפקט של הזיכרון פה, ונסתכל אפילו על הבעיה הכי פשוטה שיש. זה לא שאנחנו פשוט.
Okay, so I'll give the brief summary of this slide. What we're looking is the problem of bias estimation, and we assume we have as many samples as we want to do that, but our memory size is limited. Specifically, this means we adopt this computational model where we have a finite state machine of S states, which is initialized at some state S initial. Now, this machine, this finite state machine has some transition rule, F. You see this? Okay, F, which is an update rule based on the previous state of the machine and the current sample. So, for example, if we are in this state at time n-1, then we will go down if xn equals 1, which happens with probability theta, or we will go right if xn equals 0, which happens with probability 1 minus theta, right? Also notice that this transition rule doesn't depend on time. Every time we arrive at this state, we'll have the same decision rule. Okay, it depends only on the sample, whether it's 1 or 0. Okay, we also have an estimate function, theta hat, which maps each state to an estimate, because each state we want to output an estimate of theta. And this is also doesn't change in time. This is a time invariant function. Now, the reason we restrict to time invariant functions that one reason is because in this work we deal with upper bound, so it's natural to look at a weaker model. But another thing is that if we have a time variant algorithm, then we need to keep the time index, and this incurs a memory cost. And in our specific setting, where the number of samples can be arbitrarily large, then keeping this time index actually blows up the memory. So it will not be a finite memory anymore. Okay? Okay, cool. Now, how do we measure the performance of our algorithm? Okay, or this machine that estimates theta? We define the asymptotic quadratic risk given theta to be the asymptotic average of the instantaneous quadratic losses taken over a long period of time. Recall that we have a very large number of samples, so we have a very large time. We don't care how long we wait. We can wait very long. And we take the average and we get the asymptotic quadratic risk. And another thing that I'll mention here is that we are interested in the minimax risk of this problem for deterministic machines. Okay, so a deterministic machine is a machine like that whenever we arrived at a certain state, then the behavior depends only on the sample. A randomized machine is a machine in which when you're at a certain state, then you depend on the sample and on some external randomness, which is independent of the sample. The reason we restrict to deterministic machines, it will become more clearer as I go on, but I'll just say that you can use randomized machine and it can help, and in some cases it does help. But storing this randomness, okay, even if you have some source of unlimited randomness, storing this randomness reduces your memory budget, right? And this is something we want to take into account in our setup. So we don't sweep anything under the rug. Whatever everything that costs memory, we want to account for it in this setup. And so we define the minimax risk of the estimation problem, which is the best risk you can uniformly guaranteed over all S-state machine with deterministic state transition function. Okay. Okay, so now I want to sort of circle back to something I think you said. What would be a very simple machine to do that? So what if we have limited memory S? What is the simplest estimator we can have for theta? Does anyone have any idea? You said keep all the sequences, right? Oh, but there's something even simpler than that. I mean, you don't have to keep all the sequences because you have some sufficient statistic to estimate theta with just the number of ones, right? So we can count the number of ones in a smaller sequence that corresponds to the amount of memory you have. Okay, so this is a simple deterministic machine, which is this machine. What it does, it simply count up to m. Okay, we count m ones. How many states do we need for that? We need two counters. Okay, one for the number of samples and one for the number of ones that we see. So we start at 0. If the next sample is 0, we move right. If the next sample is 1, we move down, and so on, until we reach until we've seen m samples, and then we get absorbed and we output some estimate. It could be if we've seen 0 ones, we output 0, otherwise 1 over s, and so forth up to 1. I'm sorry, 1 over m. The size of the sequence is m. So we have m states here, and we have m states over here, right? And from this triangle shape, you can see that the total number of states is about m squared, right? So in order to count till m, we need m squared states. Okay, so what does it mean? It means that we can only have a risk of 1 over square root of s.
But now you are cheating because you're not using something. You assume that f is an arbitrary function.
If you accuse me of cheating, you better have very, very good explanation for that.
So the cheating is like that. In your model, f is an arbitrary function.
No, this is a specific function.
Here it's a specific, but the model itself, f is an arbitrary function. So the question is how you encode f. Okay? Because you need to look at all the possible functions from a state to another state. Okay? In the general setting. And then you need the memory in order to store this function. This is why you get m squared. But if you will go to another model where you're saying, no, f is a specific function, for example, the counting function, then I can implement this algorithm with 1 over s, not with 1 over square root.
What do you mean, the counting function?
The function that the algorithm is that you have log s bits.
Okay.
Okay, so you just have a single variable with log s bits.
Okay.
And you count, and the algorithm counts.
And when does the algorithm stops? When does it stop?
Take one more bit for saying I saw it.
No, but when do you stop? You need to keep the time. You need to keep track of the time. Otherwise, you'll always fill up the buffer, right? You'll count until the buffer is full, and you'll have only one estimate.
When you are at the maximum number.
What is the maximum number?
The maximum number is all the bits are 1 in binary coding. Okay. So you have log s bits.
Great.
If there are 1, 1, 1, 1, 1, everything is 1.
Yes.
Then you cannot add more ones. Okay, then you stop.
But how? You need to keep this 1, 1, 1, 1, 1. This is already log s bits. Okay.
Log s bits.
Okay, but if it's not 1, 1, 1, 1, 1, I mean.
You continue to add.
You need the timer and you need the counter.
Yeah.
And it's two counters.
You need the number of steps. You need the number of steps.
You need to count the number of steps
So
and the
2
total.
log s.
2 log s is exactly what you need.
This is what you lose, the 1 over square root.
Yes, exactly. Okay. No accusation of cheating from now on. Okay, so this is, I hope it's clear. We get some binomial variable which has expectation theta and variance which is inverse to m. So thus it is 1 over square root of s. Cool. Now, can we do better than that? I didn't say it's the best, of course, right? I said just a simple machine. And it turns out we can. And this is a work from 73 of Samaniego, where he constructed a randomized machine, okay, which is it's this machine, which has been later dubbed in the literature imaginary sliding window. And this machine actually does this surprising thing we just talked about. It can use S states to count up till S minus 1. Okay, so S minus 1 is virtually the same. Okay, so it uses S state to count up to S. How does the machine do that? If we're in state I, and the next sample is 1, then we move to state I plus 1 with probability 1 minus I over S, or we stay in state I with probability I over S. What is this rule? Why do we have this rule? Because imagine we had a sliding window, okay? And we really need to imagine it because it's imaginary. And we had the number of ones was I. So we're in state I now. Now the next sample is 1. So the sliding window moves to the right. The new sample is 1. What is the new number of ones in this window? Depends what was the sample just dropped off, right? If it was 1, it stays I. If it was 0, then it increases by 1. It's I plus 1. What is the probability that the sample was 1? We can estimate it using the empirical probability. Okay, so we use this probability to estimate whether the sample is just dropped off was either 1 or 0. And surprisingly, this, and of course, when this new sample is 0, something very similar happened. We either stay in the same state or move back one state. Surprisingly, this imaginary sliding window performs like a real window in the sense that it achieves a risk of 1 over S, right? But again, this is a randomized machine. So this risk is something that we'll call the randomized minimax risk, which is the best risk that can be uniformly guaranteed for machines where randomized transition functions are allowed. Because note that this is transition function is random. Yes? The parameter? Theta.
Yeah.
No, it's constant, but we don't know it. It can be anything in the interval 0, 1. Yes. Okay, this is not, you should email Samaniego about this. This is what we're saying. Yeah, you need bits to actually simulate this machine. But if you're looking only on randomized machine, then this thing holds, right? If we assume we have this randomness for free, which we don't, but Samaniego does, then it still holds. Now, the question is if this is tight, can we do better or maybe we cannot? So this actually was shown to be tight in a paper, seminal paper by Leighton and Rivest in 86, where they constructed a lower bound, which is for randomized machine, but since deterministic machine are a special case of randomized machine, then it also includes them. And they proved it using a tool called the Markov chain 3 theorem. I'll just mention it briefly because I think it's a pretty uncomfortable tool, I think. So basically you define the tree-weight to be the product of probabilities of three edges. And the Markov chain 3 theorem then states that the stationary distribution in state I is proportional to the sum of weights of the spanning trees of the directed graph representing the Markov chain with root at I. Okay, now this is stationary probabilities for ergodic chain, but also for non-ergodic chain, you can get a similar description. Now, in our case, recall that since all edges are some multiple of theta or 1 minus theta, it means that the risk for any machine and estimate function has this form, which is a division of polynomials. And what Leighton and Rivest then showed that from basic polynomial analysis, there must be some theta star for which this risk is greater than 1 over s. Thus, the randomized minimax risk is greater than omega of 1 over s. And this closes the gap for randomized machine, right? We have an upper bound of Samaniego, a lower bound of Leighton and Rivest, and we get this, and actually this problem is closed for randomized machine. Now, in the same paper, Leighton and Rivest also considered deterministic machines. And what they did was the following. They took this construction, the randomized construction here, and they did what you mentioned. They simulated using a deterministic machine. They de-randomized this construction using Van Neumann extraction. Okay, so yeah, everyone knows what Van Neumann extraction is, or should I mean? Okay, so this is basically a way to simulate a fair coin toss from biased coin toss. So you can use one of these branches, simulate each branch simulates some multiple of half. So this simulate 1/2. These two branches simulate 1/4. These three branches simulate 1/8, and so on. Okay, I mean, there's the way it simulates. I mean, I don't have too much time to get into it, but this is what it does. Now, since the machine, the randomized machine, the transition probability has some multiples of 1 over s, then we want to simulate, in order to simulate 1 over s, we need log s branches like this per each edge. So it means the amount of states is growing by log s. Okay, so in order to achieve the same risk, we need log s time log s states, or equivalently, I can say that with s states, we can achieve risk of log s over s. Okay, so basically what this machine does is taking some Samaniego machine, and each edge, we de-randomize it using about more or less log s states times 3, okay? But that's what it does. And we get this upper bound on the deterministic, on the risk of deterministic machines. And they concluded this part of their work, Leighton and Rivest, I mean, by formulating the following conjecture, is that this risk, log s over s, is the best risk that can be uniformly guaranteed for deterministic machine, okay? Which means that this is truly the minimax risk of deterministic machines. Now this is I think quite intuitive for them, because they take the optimal algorithm and they de-randomize it, and they say, okay, what we got is probably also optimal. And our main result in this presentation and the corresponding work we submitted to COLT is disproving this and showing that for deterministic machine also the fundamental bound is 1 over s, which means we construct an algorithm, okay, which achieves the 1 over s upper bound. Okay, so before I get into our construction, any questions about what we discussed so far? This is the background for our work. Okay, I was hoping someone else so I could drink some water. Okay, so let us give a high-level approach of our algorithm. And what we want to do is actually want to construct a chain that have a strong drift towards state who has good estimate which is close to the real value of theta. What we want it to happen for all theta, right? Because we want to uniformly achieve that. However, in deterministic machine, the transition probabilities are only theta or 1 minus theta, right? So we cannot get a different drift for each theta, okay? What we achieved actually is simulating these edges by using mini chain. So each of these edges will be a mini chain of some number of states. We will be able to simulate the drift, the strong drift that we want. And as a result, we will get a new chain whose state space is smaller. And I will refer to this chain as the sampled process. Okay. Now, continuing with this high-level approach, basically what you do is that, right? I mentioned mini chains. So it means partitioning the state space into k disjoint sets, where the estimation in each for all states in this set is the same. Okay, for all states in the set get the same estimate, theta hat of k. And our goal is that given theta, the stationary distribution of our process Mn will be estimated on states whose estimator is closest to theta. Now, of course, I mentioned this is a Markov chain. It's clear that a finite state machine induces a Markov chain, right? This is, I hope it's clear. Now we have a trade-off here, and the trade-off is this. Let's say we have k sets, then our risk must be at most omega of 1 over k squared, because there must be at least some theta in the unit interval at distance omega of 1 over k from all estimators. Right? Yes, okay. So what I'm saying is this. We have, this is the, so this is the unit interval, 0, 1. Let's say we have k estimators. So this is theta 1, I don't know, theta 2, and this is theta k, okay? Now there must be some point which is a distance 1 over k from all points, or half 1 over k, right? So if, for example, if theta is here, then it will be this distance from all of them, right? And if theta is here, then it will be a distance whatever, right? Okay, so of course we can only achieve this omega of 1 over k squared. So we want a large number of sets. We want a lot of sets. However, we'll need a lot of states in each of these sets in order to simulate the strong drift. Okay, this is more of an intuition, right? Because with just one state, we know we can't simulate any drift. So we need more states. So this means we want small k. So we have two competing requisitions, and we find out that actually choosing k to be about square root of s balances these choices. We can get a strong drift, and we can achieve the 1 over s bound that we want. Okay, so I'll go now into the specific construction, right? And please stop me at any time if you have questions, but you're already doing that. Okay, so we define something that is called a nested Markov structure. Okay, so before I'll get to that, I'll want to define a quantized process. What is this quantized process? This maps each state to its set labels. So recall we have sets where all the states in the sets have the same estimator. So it seemed natural to define this process. Okay, so what does it mean? All states in the first class get the label 1. All states in the second set get the label 2, and so on. Having defined Q and thus, we can describe it in a run-len form, which means runs of the same letter. Okay, so we can describe Qn as ai and tau I, where ai is the first letter in the ith run, and tau I is the length of the ith run. Okay, so ai in our construction is just the class label. Okay, and tau I represents how long do we spend in a class. How much time do we spend in each class? Okay, and we refer to AI as the sampled process and to tau I as the holding times process. Okay, and we can describe the Markov chain with this in this form, right? We get to a new class. I just give you the label of the class and how long you spend in this class. For the estimation process, it doesn't matter since all states in the class have the same estimate. Now, in general, this process can be complicated, but we make some assumptions that help us, that actually make this much easier. One assumption is that all the classes Sk are accessible from all other classes, okay, which means not necessarily in one step, but there is some path from any set Sj to any other set Sk, okay? And also to each class has a specific entry state such that all edges that go into this class go into the same state. What does this ensure? This ensures that, first of all, the original Markov chain Mn is ergodic, right? Because everything is accessible. But also that this process, AI, the sample process, is also an ergodic Markov chain. Okay, so we have an ergodic Markov chain AI, and also this tau I, dependent on AI, dependent on the class that we're in, is independent of the whole path. And we can denote the conditional distribution of tau I given AI equals k as P sub Tk. And for convenience, we define Tk to be some holding times distributed according to P sub Tk. So what does it mean? We get at a certain, let's say you look at this process AI, going into a certain state, okay, corresponds to getting into a certain class in the original chain. So I'll give you the number of the class, and once you arrive there, you flip a coin with probability PTK, and that determines how long you spend in this class, right? And each class has a different distribution depending on the construction of the class that we choose. Okay, so we call all of this construction, we call a nested Markov structure. Okay. Now, how do we measure the performance of this Markov structure? Recall that we have this asymptotic quadratic risk, right? Now, since everything here is ergodic, then this time average actually converges to to the average over the stationary distribution of Qn, right? Since the estimator only depends on the label of the set, then we can write this in terms of the stationary distribution of Qn, right? And Qn is also a stationary and ergodic process, since it is a deterministic function of Mn, which is a stationary ergodic process as well from construction. Okay, now what we show is that we can write the stationary distribution of Qn in the following way, and I will explain what we have here. So we have pi k is proportional to mu k time etk. Mu k is the stationary distribution of the sample process AI, and etk are the expected holding times. Okay, so what is pi k? It's the stationary distribution of Qn, okay, which is, from ergodicity, we can think about it as the average fraction of time we see the letter k. What is the average time we see this letter k? It's the stationary distribution of the state k in the sample chain, the average time we spend in this state, right? And of course, we need to normalize. Okay, so of course, this needs to be proven, but it's a pretty technical lemma, and I will not go into it. But it sort of induces a nice expression, since we see that the risk depends on this stationary distribution, and this depends only on mu k and E of tk. So that means that if we can construct a machine such that these two conditions hold, we'll get a small risk. What are these conditions? First condition is that mu k will be concentrated on states with good estimates. And second is that the average amount of time we spend at states that has good estimate is not smaller than the time we spend at other states. Okay, there was a question, yeah. Why? That depends how we construct the mini chain. I didn't. I mean, until now we just said that we construct a mini chain, but I didn't tell you how we construct them. Okay. Okay, but basically what we say, I'll maybe just. So we have the original process Mn. None of these work. Okay, which is some states 1 I S. Okay, and what we do is sort of we lump a bunch of states together. So let's say we lump all of these states are the set S1, all of these states are the set S2, and this is Sk, right? And we map all of them to just a new state, a new Markov chain. Okay, and this has some transition probabilities, whatever. And this is an ergodic Markov chain. Okay, but whenever we get to one of these states, we flip a random variable, which is denoted by T2 and T1 here and Tk. And this is the amount of time that we spend in each state, right? So these two, this description of the sample chain, okay, this is sampled chain, and holding times contains all the information relevant for estimation. Of course, something gets lost because we don't know in which state we are at the particular set, but it doesn't matter for us because all of these states have the same estimate. Okay? Yes.
Just not sure I'm following. What you're trying to do is do like a different de-randomization of the imaginary window, or this is like a completely new?
This is something else.
Like a completely new.
What we're trying to do is we want to, okay. Let's consider this machine, okay? And recall that we said that what we want to get is the k is about square root of s. Okay, so that's square root of s state. What we would like to do is let's say that the closest estimate to theta is theta 2. Let's say this is the closest estimate to the real theta. So this is almost theta, right? We would like to have a stationary distribution that looks something like this, okay? That will be very much concentrated in this state. And now if you plug in a different theta, let's say such that it's more like theta 3, then we want to have this stationary distribution. So we want for each theta to get this behavior. And how do we do that? We use the mini chains which have not yet specified how we construct them. This is the next slide, okay? So
to answer the question, so the randomized chain induces a binomial distribution in this set of chains. Of course, it's still depicted in the right place, but the standard deviation is greater. There's less state. The concentration is not better.
But this has nothing to do with the imaginary sliding.
We're not simulating.
Yeah, it's a different because that one didn't. I mean, for deterministic machine, we already know if you de-randomize it, you get logs of.
Maybe there's like a better de-randomization in the context. I mean, can you take the imaginary window and with some kind of better de-randomization get something that is.
Yes,
Okay. Because you need the random point flips in the sliding window of resolution of 1 over s. So you need to generate random variables with the denominator 1 figures. You cannot do this with less than log s fixed.
Yeah, generally, but maybe for like this specific construction, you can use randomness less often. I don't know, but this is not what they're talking about.
And I doubt that there is a machine that looks very similar to the slide that we achieved you would not pay price.
Okay, so the last thing that I need to give you is that how we construct these mini chains, and explain why this truly holds. These two conditions will actually hold for our choice of mini chain. Okay, so we choose the classes SK to be mini chains that perform a composite binary hypothesis testing. And for this, we'll introduce something that is called runs NPQ. Runs NPQ, this is an n-state machine which decides between hypothesis theta greater than P versus theta smaller than Q for some Q smaller than P. How does it make its decision? It looks for consecutive runs of either letter. So for example, if we see a long consecutive run of ones before a long consecutive run of 0, we decide on theta greater than P. Otherwise, we decide on theta greater than Q. Okay, so this algorithm can be implemented using this finite state machine. Okay, so see, we're looking for a run of ones which is of size n minus s, small s, or a consecutive run of 0 of size s. And whenever a run is broken, we go back to the origin and start counting again. This the initial point s is chosen to optimize the error probability of this machine. I'll mention this is a machine that we introduced in a paper from ISIT 20 on a work on binary hypothesis testing with finite memory. Okay, so over there we use this machine as to get an upper bound, and it turns out that it's very helpful in this problem, because what we do is we choose our mini chains SK to be NK states machine that solve the composite hypothesis testing problem, theta greater than letter case k plus 1 over k plus 2 versus theta smaller than k over k plus 2. Now, the k plus 2 in the denominator instead of k is just for technical reason, because we have some problem dealing with probabilities at the edges of the simplex, but k plus 2 or k, it's the same order, so we can think about it as k. We decide between two hypotheses who are 1 over k apart, or distance is 1 over k, right? And the time it takes to make a decision, the time we spend in this mini chain in our formulation is p sub tk. Is distributed according to this distribution. Okay, so what makes this machine so good for our purposes? It's the following lemma, which is simply a technical analysis of this, analytical analysis of this machine. So I will not show the proof here, but what we show is that this machine can decide between the hypothesis p equals something and q equals p minus 1 over k with constant error probability at most epsilon and number of states which is about O of k states. Okay, so with about k states, we can decide between two hypotheses which are a different distance 1 over k. Okay, so what do we get? We have k states here. Each of these edges is about k states also, because this is one of the mini chains. So we can get a machine with s states, right? This is about square root of s, and this is also square root of s for each edge. And the drift that we discussed about earlier comes from this point, okay? So basically what this machine is doing is we test between hypotheses that are distance 1 over k. And as we traverse the chain, we move this test. We move over 1 over k always on the interval. And if theta is in this interval, then the probability that it goes away from it, either right or left, is smaller than epsilon, right? Okay, so basically what we get is we have I forget that this is working. This is the interval. We divide it to interval of size 1/k. And if theta really sits somewhere over here, then what we'll get is that the corresponding in the machine, okay, the corresponding sample machine, the probabilities that go away from this state will be epsilon. And the probabilities that go into that will be 1 minus epsilon, because these will be the error probabilities of the hypothesis testing, of the composite hypothesis testing, right? Because going right means that we decide that theta is greater than this value, which is an error. So the probability for deciding that is smaller than epsilon. Okay, so this is the mini chain construction. This is the number of states. When we sum over all the total number of states, we get that this is order of q squared. Thus, k can be about square root of s. Yes, some questions. No, epsilon is a constant. Yeah, but you don't want it, you don't need it too small. You can just choose it to be 1/3, right? Or 1/100, right? I mean, it's, as long as it gives you a drift, right? You just need it to be, to get a drift, you just need it to be smaller than half, right? Yes.
Maybe, okay, so how does the number of samples that you need at the end depends on this, say, epsilon or I mean, I guess you lose samples with respect to kind of the simplest machine with the one verse for the best estimates, right? Because you're kind of using samples for the randomness.
You're talking about the constant of this?
So you're analyzing, yeah, sample. I mean, at the end of the day, yeah, you're analyzing when n goes to infinity.
Right.
But how fast does this happen?
How long does it take to converge? Probably very long. I mean, I think it because these because where did I get? Okay. This is the mini chain. You're looking for a consecutive run of ones, okay, or 0, and this is about square root of s. So you need to see a very long consecutive run of ones, so you can wait for that a very long time. Okay.
So I'm paying in the sense in sample complexity for this.
You're paying, yes. So, right, because we assume the number of samples is arbitrarily large, then we also assume that you can wait enough time to see this amount of samples. Okay, and if the samples come in a very long rate, then it, yeah, but it takes a very long time, I guess.
We really analyze them in some terms. I'm not sure it's sample complexity out of the formulation, but this chain can take a long time. But once when you're very far from the true data, it will convert very fast. You will see the one sequence.
I think it's exponentially. I think it's still exponentially less in S or something.
Because the time is very. The max is very. Anyway, yeah, it's out of the. We didn't analyze it. It's definitely not for a constant.
Yeah.
For example, it's definitely not optimal. But,
right.
I'm not sure the mixing time is that terrible.
Yeah, we can think about it. Yeah, the extreme states are not a problem, but as you get closer.
When you get closer, it starts.
Yes, that's okay. So let's just summarize what we just said about this mini chain in a second. So with this construction, with this choice of mini chain, we get the following sample chain. We set the estimator to be simply, if we're in state I, then I over k. The sample chain actually is a random walk. We move only one state left or right because maybe I forgot to mention the way this the way this machine works is that we test for H0 and H1. If we decide in favor of H0, we exit right, and we go to mini-chain SK plus 1. If we decide in favor of H1, we go left to mini-chain SK minus 1. So in the sample chain, we only go one state right or left, okay? And due to the construction, we get this strong drift, which means if we are far from the correct interval, then if the interval is over here, then the drift over here is at least 1 minus epsilon. And if theta is over here, then the drift to this direction will be at most epsilon, right? Okay, and we choose epsilon to be some constant smaller than half. Who do you, yeah.
I'm wondering about the edge cases. It seems like you mentioned that you had problems with it, and it seems to be kind of maybe the easiest.
No, yes, but it is simple. You're talking about 0 and 1.
Close to 0. Like one theta is close to 0 and 1. Right? Very close. Less than 1 of the 3.
Yes. Yeah, but the problem is that with this, when we write the proof for this machine, we need to assume p is greater than 1 over k. We have a different proof which is very simple, but it's not a real problem. It's an imaginary.
Trying to balance the probability of getting to each one during the middle. Right? Once theta is too small, and you can only use one length. So you need at least one, size 1. If theta is too small, it's hard to balance.
Okay, how much time do we have? 5 minutes? Okay, so we arrived at the technical part. I'm not going to go through all of it, but maybe just to do one little math thing, just that that I'll feel like I convinced you of something. Recall that. So we got this strong drift, but in order to convince you that this machine actually works, I need to convince you that these conditions hold, right? That we have a concentration of stationary distribution and the expected times are not too bad. So I'll just show the proof for this first one because it's a very simple one. So what we want to show is, again, if theta is in the interval k over k plus 2 and k over k plus 1 over k plus 2. So if theta is somewhere here, then the stationary distribution to the left of state k minus 1 decreases exponentially or geometrically with a rate which is at least epsilon over 1 minus epsilon. And the same thing goes when we look to the right. Okay, so if this is the correct value of theta, okay, let's say theta is in this interval, then the stationary distribution of states over here and over here decreases like epsilon times 1 minus epsilon. Okay, this is the rate. Okay, so how do we show that? A simple fact, this is actually a lemma, but it's very simple. For any stationary process over alphabet S and partition C and C prime, the probability that xn is in C, and in the next moment xn moves to C prime, equals to the probability that xn is in C prime, and in the next moment move to C. Okay, it's a sort of equilibrium equation. Now, in our specific construction, this is a very simple expression. If we partition our state space where C is states 1 till I minus 1 and C prime is I till k, then how can we write this equation? The probability of being in C and moving in the next state to C prime is simply mu I plus mu I minus 1 times pi minus 1. And the other side here is mu I times qi. Okay, so this is immediate from this fact. Now we can use it recursively, right? Because we can also use it, we can make many such partitions. So using it recursively, we get the following product, mu k minus I equal to this product. And if I is smaller than k, then what does this q? Is the probability to go away from the correct interval. So it's at most epsilon. And pk is at least 1 minus epsilon. So all of this is upper bounded by epsilon over 1 minus epsilon to the power of I minus 1. And something similar happens when we look at states to the left, to the right of k, right? We get this product, and this time pk is smaller than epsilon, and q is greater than 1 minus epsilon. So we get this expression over here. Okay, and what we show is that, and I will not go into the next one, which is the expected holding times condition, but what we show is that we spend most of the time in the correct states, because this is the regions where the decision of the mini chain is the toughest, because it's really where the correct value of theta is. At other values, theta is very different from the values that we're testing again, so the test goes faster. Okay. Okay, but we don't have time to go into that one, so I'll just let you ask questions if you have any more left, or make any comments and whatnot.
Can you explain again what does distributions do? Like, I understood them just count consecutive appearances of the same.
Yes.
Intuitively, that it sounds like a really bad idea.
If you're in a hurry, then it's a really bad idea. But if you have, as we said, if we have a lot of time, then it's not such a bad idea, because what it does, it separate events which are the most rare. Okay, so think we have a limited number of states. We want to separate between two hypotheses. Because since we can wait, then I'll tell you, just wait for the events that distinguish the best between the hypotheses. And such possible event, is a long consecutive run of ones. You just wait until you have a long run of ones or a long run of zeros. And once you've seen it, you're fairly convinced that theta is greater than this value, or theta is greater than p, or smaller than q. Okay, so again, when time is limited, this is not so good. When memory is limited and time is not, then this is not so bad. Okay.
Okay, thank you. And if you abstract out the unit chains and focus on the standard chain, can you want it to function like explicitly and compare it with a chain from the 70s? Like there's the optimal one is a non-deterministic approach.
So you mean if you look at the sample chain, then what?
And abstract out the unit chain.
Oh, yes.
Can you write explicitly like the transition function between states and compare it to the
you mean
chain?
Well, we have, what we know is the transition function is at most epsilon, right? So it's pretty close to epsilon. I mean, if you take it's not I think it's pretty tight, so it's about epsilon, but the probabilities are, you get an exponential decrease. So in a sense, it's better than over there, because there, like O said, there's a binomial, you get a binomial distribution. So your standard deviation is about 1 over square root of s or whatever. Okay, but here your standard deviation is O of 1, because this is exponentially decreasing. So you really concentrated in the good area of the estimators.
Okay, so thank you again, Thomas.